Okay, so I'm going to do a number of things. And let me begin by saying that I am a historical realist, but maybe not a scientific one. That is to say, I do think that there are ways in which the historical material is conducive to thinking about historical accounts as not merely verisimilitudinous, but actually strongly realist. And I base that on two things. One, consistency with existing evidence, but two, especially if you're doing something technical, if you have really come to understand the way in which a particular scheme operates, you ought to be able to predict the way in which a particular problem that you have not read a paper on, a historical problem yet, will go. If you cannot do that, then you haven't produced a reasonable, if you will, account of what went on. And the historical record may be finite, but it's huge. And nobody really working in any particular area has probably read every single thing that continues to exist in that area. So it's possible to find things that work that way. And what I'm going to do today, and let me apologize from the beginning, I'm going to be extremely technical, because that's the only way that I can show you how, in this particular instance, a scheme that was grounded, if you will, on the conception, in some sense, that the world is a continuum and that all entities in the world are in some sense parasitic upon the continuum, worked to generate a practice in electrodynamics, particularly in Britain, though not only there, in the period between about 1873 and 1895, which led to very concrete results. And it had a certain way of handling things, and that way, aspects of that way passed down into later electrodynamics and other aspects did not, and that it was confronted with and indeed generated, in a certain sense, a series of empirical investigations. So let me begin this way. I'm going to be talking about numbers of people who I'll loosely call Maxwellians. This is Mr. Maxwell himself all up there. And the ones that I will mostly be talking about today are these people here. George Francis Fitzgerald, Henry Rowland, the American, Richard Tetley Glazebrook, head of the first Institute for the Physical Research on Parameters here in Britain, J.J. Thomson, of course, and collaterally, John Henry Poynting, the strange Oliver Heaviside, and Joseph Larmor. But there are other people who will feature in what I'm about to talk about, so I outline those as the Maxwellians. Lawrence will come in a little bit later, as will Paul Drude, a great German physicist. Then there are the experimentalists. That is, people I characterize as experimentalists because the effects that they discovered were not necessarily deeply connected to any particular physical scheme, though they were influenced by them. There was John Carr, worked in Kelvin's laboratory over in Glasgow, and discovered what was rapidly called the Carr effect. There are actually two such effects. John Hall over in England, in America, sorry, let me go back. Hall in the United States, a student of Rowland's, and finally, Peter Zeeman, discoverer of the Zeeman effect. And I'm actually not going to talk about the Zeeman effect, but what, in effect, led, so to speak, led up to it. So let me begin by kind of compressing the way Maxwell's equations appear in the treatise. And in order to do this, I will, of course, use modern vector notation, though he doesn't use that mostly in the treatise. He uses it a little bit here and there. But for the cases I'm talking about, it doesn't make any difference. And the reason it doesn't is because the equations that are used, though they're usually only given in the first Cartesian component of them, are nevertheless fully equivalent to what I'm going to show you, number one. And number two, these people were able to run changes in their head which almost no modern physicist can run today because they were so used to dealing with what we would call component forms of vector equations. So I'm just going to run through these quickly. There is, first of all, in the treatise, very important relationship, namely the zero divergence condition on the so-called magnetic induction. On the basis of that, and this dates back to Faraday non-mathematically, a quantity called the vector potential, A, was introduced over here, which is fundamental in the way Maxwellians worked with the treatise. The vector potential after Heaviside was sort of pushed to the side until it came back of great importance in quantum electrodynamics much later. But it's central to the way Maxwellians work, and I will show you that. Then there's what I will loosely call the Faraday law, namely the generation of an electric field by the rate of change of the vector potential, or the magnetic induction, if you will, plus the scalar potential here, which won't feature in what I'm going to talk about today. The Gauss law relating the divergence of the electric field to the density of charge. Charge is a complicated thing in Maxwell's electrodynamics, which I will come back to in a moment. Finally, not finally, but penultimately, these relations here, relationship between magnetic induction and magnetic force, H, namely the vector that you use to actually calculate the forces between current-bearing conductors or magnetically affected bodies. The relationship between electric force and something called electric displacement. That's a concept that really is developed first by Faraday, very significantly so, in an effort to divorce the way he was thinking from the notion that electric charge should have any substantial existence. Just to compress everything very quickly, in Faraday's way of thinking, charge is an epiphenomenon of something else, which I'm going to mention in a moment, and that gets encoded into Maxwell's treatise and is picked up by the people I talked about as they studied the treatise and learned to apply it to different types of problems. And that leads to totally different ways of treating problems from the ways that people who thought of charge as having a substantial identity. And by substantial identity, I mean that if you were to calculate the total amount of charge in the universe, for instance, on Maxwellian ways of thinking, that could be completely zero. It's not preserved. On substantial ways of thinking, charge quantity is actually preserved because it has substantial identity. That leads to different understanding of the so-called equation of continuity, and the result of that is different ways of solving problems, which I'm actually going to show you some of in a moment. Then there's the relationship between the total current, that is, that which can produce magnetic fields, and something called the conduction current. And this, of course, is what Maxwell is famous for introducing, the rate of change of this displacement quantity here. The conduction current is the undeveloped, mysterious thing in continuum electrodynamics. I'll talk more about that in a moment. But it is empirically related to the electric field by Ohm's law through the conductivity sigma. Now, just a footnote, the reason that the conduction current is mysterious is because the conduction current, when it exists, dissipates energy. And that which dissipates energy cannot be incorporated in what I'm going to describe as a dynamical scheme grounded on the central principle deployed by the Maxwellians, at least those who were trained at Cambridge and somewhere else, namely Hamilton's principle. It is the deployment and use of Hamilton's principle that is the groundwork of Maxwellian electrodynamics in a continuum scheme, and it's when that fails that continuum electrodynamics fails as well. And that's what I'm going to take you up to. So I'm not talking here about the reality or non-reality of the ether. Of course, they all believed in the reality of the ether, so what? It doesn't make any difference, actually, in this sense. It's the system of it's the system of practice for attacking how you attack problems that's at work here, and that is, of course, connected to whether there is a continuum structure in the universe or not, but not to questions of reality or non-reality. Helly wrote a paper fairly recently on the grand equivalent to modern string theory in the 19th century, namely the so-called vortex theory of atoms. Now, one of the things that that's characteristic of that is it doesn't generate anything new. You can't solve too many problems. It's even hard to generate, to get back the relationships in kinetic theory from that sort of thing. And you don't find any real attempts, with the partial exception of J.J. Thomson, to use that thing to actually solve existing problems of other kinds or generate novelties. And if you can't generate novelties, I mean, this is what physicists do. You have to solve problems, you explain existing effects, and most importantly, you look to generate new ones and solve those things. If you can't do that, it's, you know, you're sitting there whistling in the wind. It's not going to, it's just not what physicists do. It's their practice. Finally, in the set of equations, the Ampere law, which relates the magnetic force to the total current, which we'll see more of in a moment. And then, very significantly, because since this is grounded in the notion that the continuum, if you will, has a distributed energy in it, what Maxwell calls electrokinetic energy, which he expresses in two ways. First, as the vector product of the vector potential, scalar product of the vector potential and the total current, which then, if you integrate out to infinity, there's a little bit of an issue with that, by the way, because Heaviside hated this form, but he liked this form. If you integrate this out to infinity over a surface, you can express it in terms of the scalar product of the magnetic induction and the magnetic intensity. And then finally, the so-called potential energy, which is the scalar product of the electric intensity and the electric induction, displacement D. And one is called kinetic and the other is called potential because one figures in with a positive sign in Hamilton's principle and the other figures in with a negative sign in the principle. And that's what distinguishes the one as kinetic and the other as potential. Of course, they do think it has something to do with motion, but they don't do much with that. Now let me talk about some of the key assumptions shared by Maxwellians. Since this is a continuum, everything is treated as a continuous variable. That means that electric permittivity, magnetic permeability, and electric conductivity, these are the three things which entered in those equations I showed you a moment ago, they are not treated as things that you build up out of microscopic relationships between particles. Not at all. They're treated as continuous parameters. Now, if you were to ask a Maxwellian, and I can find evidence for this, well, but you know, there are particles in the world. You might say, yes, but the particles themselves are epiphenomenon of the continuum, and if you go down to the particle level, if you went, you know, from the left side of the particle through it to the right side, those factors, those parameters would vary continuously. So at a microscopic level, you're averaging, but you're averaging over things that have actually varied continuously at a microscopic level, if you will. And then they don't do anything at the microscopic level anyway. So these are considered to be properties of the substrate. I will try and avoid the use of the word ether, and can be modified by the presence of matter, only we have no theory as to how that happens. Very significant. All electric currents are considered to be displacement currents. I'll show you how that works in a moment. These things are conservative in dielectrics, dissipative in conductors, and that means that strictly speaking, the C, the conduction current, is an epiphenomenon of displacement itself. It's not a flow of particles or anything like that. It's actually an epiphenomenon of displacement. I'll show you how that works in a second. And then, and this is the most important thing, those field equations I showed you a moment ago, the Maxwell equations as they were then, are not sacrosanct. They are to be deduced. And they are derivative of the most fundamental thing, which is the expressions for the field energies that occur in the continuum. And I'm going to show you how that goes in a moment. So, and this is one of the major things that distinguishes this practice from well, really post-Lorentz electrodynamics, namely that Maxwell equations are not fixed. They are to be deduced, or at least some are. And what does that mean? And I'm going to show you how in a moment. It means that one of these two fundamental laws here will enter Hamilton's principle as a constraint, on the variation that's involved there. And that constraint, when stuck into Hamilton's principle, will generate the other one. You can choose either one. They normally choose this one to be deduced, and this one, this one to be deduced, Faraday, and this one, Ampere, as a constraint. So the whole technology, if you will, of the mathematical structure is grounded in an image of the continuum and so on, but it is fundamentally situated in the priority of Hamilton's principle and energy expressions. Now, I said that the conduction current is an epiphenomenon. How does that work? Well, Maxwell's actually very explicit about this in the treatise. And interestingly enough, in Britain, this was widely understood very carefully. I have never found an instance of somebody in France or Germany who actually ever picked this up. And that, I think, is primarily because they mostly, well, not mostly, none of them really learned electrodynamics out of Maxwell's treatise, whereas there are a fair number of people in Britain who do. Most of the people I mentioned a few moments ago as Maxwellians were born in the 1850s, mid-1850s. That means they were, 17, 18 when the treatise came out, and they studied it directly. Now, even today, if you take standard set of Maxwell's equations, if you have a leaky condenser, which is a capacitor, and with the material in between the two plates having both electric permittivity, permeability, and conductivity. It's a leaky condenser. It's like if you had moist air in between, for instance, okay? And I charge the thing up with a voltaic pile, and then I disconnect it. Then what happens? Well, what will happen is the charge on the plates will gradually disappear, bit by bit, as you get flow through the structure, we would say. What the Maxwellians say is that displacement has built up when you charged it up, and that displacement gradually decays away. Now, what does that mean? It means that even today, actually, if you run the equations through, a decaying, an originally charged decaying condenser, as the charge decays away and the energy dissipates, does not generate a magnetic field. That is, in fact, true. It does not generate a magnetic field. And the reason for that, we would say, is that because of the zero divergence condition on the total current, in this case, if you have leakiness, the conduction current is always exactly equal and opposite to the displacement current. So this is correct. But Maxwellians built an entire way of thinking on this. And just to show you why it works that way, because of the relationship between D and E and C and E through sigma and epsilon, you have this relationship between D and sigma involving, between D and C involving the conductivity and the permittivity. Then by the zero divergence condition, following from the Ampere law on the current, you get this. I know I'm being fast here, I just wanted to show you this, which leads to this result here, namely that the divergence of D decays over time exponentially, but the divergence of D from the previous set of equations is in fact charge density. So the charge density decays. And the result of that is if you have an interface across which the ratio of sigma over epsilon changes, then at that interface, over time, what happens is a decay. And if sigma over epsilon is huge on one side, like in a conductor, but really small on the other side, then eventually, in some period of time, one becomes so small that you can't measure it, and the other one stays very relatively large, although at an infinite time it'll all decay away, which is why charge may never exist at all in the universe at some point, can all decay away. And the result of that is that all charge is an epiphenomenon of displacement, and consequently the conduction current itself is nothing but the epiphenomenal relationship representation of displacement decay. Now, how does that work? Well, J.J. Thomson once said, well, if we had really fine measuring devices, we could look, and Maxwell actually said this too, we could look down, way down, and we would see that in a conductor where a current's flowing through, what's happening is displacement is building up and decaying away billions of times a second. So that's the, if you will, the theoretical imagery behind it, but you can't touch it. Now, where does this all take us? Never mind that for a moment. This way of thinking, grounded on energy, Hamilton's principle, and the priority of displacement, is used first to explain an effect that was discovered by Faraday and linked light and electrodynamics in 1845, namely the so-called Faraday effect, and subsequently to deal with three other effects that were discovered during the existence of Maxwellian practice. Now, the Faraday effect is that if you linearly polarize light and you send it through a dielectric, usually carbon disulfide, which is subject to a powerful magnetic field running along the axis of it, that the plane of polarization will be rotated, and in a very specific way. If you reflect it back, the plane of polarization rotates back again. Okay? Excuse me, the plane of polarization continues to rotate forward. I made a mistake for a second because I wanted to distinguish it between what happens if you pass it through quartz. If you pass it through quartz without a magnetic field and reflect it again, it rotates back as though there were a screw there. But in this case, and this was Faraday's suggestion, that must somehow reflect the existence of a rotation, of a velocity rotation in the medium so that it continues to move it. Now, Maxwell produced the first theory of this. Well, actually, it's the second, but the first one was done in France and on a totally different basis. And his theory is stuck at the back of the treatise. And what did he do? It's not an electrodynamic theory as it stands, but it is one of these continuum theories, which is grounded in Lagrangians and so on, and that's going to form the basis of what I'm going to show you in a few moments that Maxwellians did. He assumed, first of all, that the magnetic field has spin, or at least that in the equations that he's going to develop, the magnetic field that you apply can be treated in the same way that you would treat spin in a continuum, vorticity. That the system of equations that he's going to use is the same ones that govern an incompressible inviscid fluid. No viscosity. Viscosity is dissipative. And that the light passing through alters the vorticity slightly. And the result of that is this complicated looking result for the kinetic energy that is produced under these circumstances. Now, what have we got here? This du dt is the velocity of a part of the medium. It's a continuum. Here we have the applied magnetic field, and here we have the curl of this velocity. This is a very important expression. It's grounded in a continuum notion, but there is no, how shall I put it, there is no explicit discussion of the structure of the medium in question. It's simply treated as a continuum, and that it's governed by the same equations as the Navier-Stokes equation, but without viscosity in it. You don't have to know anything more about it, which, by the way, generated a series of really antagonistic remarks by an American philosopher by the name of J.B. Stallo, who thought that that way of thinking was completely incomprehensible because there was no structural discussion of what exactly the constitution of the medium would be like. If Stallo had been paid attention to, by the way, continuum analysis altogether would have to have been thrown out. Now, if you add this to the usual kinetic energy of such a system, and you make an assumption concerning the expression for the potential energy, and you stick this in Lagrange's equations, you come out with a wave equation. This is the wave equation Maxwell developed for the Faraday effect. This would be the wave equation without a Faraday effect, the same one that you would get in an elastic continuum without viscosity. This is the displacement of the fluid. And this is the term that gets added in there as a result of the existence of the external magnetic field. Now, everything that I'm going to talk about now, all subsequent equations of the effect have this general form. It satisfies all of the empirical discoveries, of which there are quite a few about the Faraday effect, by the time that Maxwell has published this thing. So what we're going to look for then is the structural patterning of subsequent deductions that lead to something that looks like this, or that has the same form as that, but in which the variables take on different significance. They take on electrodynamic significance. Okay? And I'm going to go through that, show you the changes running on it, and then I'm going to show you how it all fell apart. It starts with the discovery of a new experimental effect, the Carr effect. Now, this is discovered in 1878 in, as I said, the laboratory of Kelvin in Glasgow. Now, Kelvin is antagonistic to Maxwell's electrodynamics. Kelvin does think in continuum terms. He doesn't buy the notion of the displacement and conduction as a displacement current the way Maxwell does. Some complicated reasons for that. But he is running one of the first research laboratories in the UK, actually anywhere at the time. And John Carr, who is not a mathematically deeply adept but a fantastic experimentalist, had 3 years before discovered another effect, which we now call electrostriction, in which if you compress glass, it generates a birefringence in it as though it were a piece of crystal and so on. And he pursued playing with light at Kelvin's instigation, and in 1878 he discovered the single most important effect that had been discovered in optics since maybe the discovery of polarization by reflection by Malou in 1809. And the reason for that is that the Carr effect implicates everything at once. If you could solve this effect, you could solve every problem in electrodynamics. Okay? And so it attracted a lot of attention. So what is the Carr effect? If you take linearly polarized light, or it could be elliptically polarized, but for simplicity we'll take that, and you reflect it off the surface of a metallic body which is subject to a magnetic field. The magnetic field can be perpendicular to the surface or in the surface. The light gets reflected off, and when you measure the light, you find that the linear polarization has become elliptical, and that the major axis of the ellipse has been rotated away from the original direction of linear polarization. There's two effects there. One, ellipticity, and two, rotation away. Right, now I'm going to tell you right now that there is no way to get this without introducing conductivity into here. But you can get some of it. And let me now show you what was done. Let me reiterate, it's the most significant experimental discovery. Really, I think I'd include Faraday, which is a subset of this, because it involves all three electromagnetic parameters: dielectric and magnetic capacities and electric conductivity. Now, the first use of Hamilton's principle in field theory was for this problem, along with the Faraday effect. It was done by George Francis Fitzgerald in 1879 and was, by the way, the very last paper that Maxwell, before he died, refereed for the Philosophical Transactions of the Royal Society. And he appreciated the deduction, but he didn't believe it, but for other reasons that I'll tell you in a moment. There's a certain sense in which Maxwell was not fully a Maxwellian. This is not unusual, you know. The inventor of a scheme sometimes doesn't carry it forward fully in the same way that the acolytes do subsequently. All right, so now I'm going to show you what he did. First of all, he introduces the magnetic field directly, but instead of identifying it with vorticity, he identifies the H field with a velocity. He just calls it a du dt with the u uninterpreted. Uninterpreted. You just call it du dt. I mean, who knows what's going on down there fundamentally? But it's got to be treated as a continuum. And then now he's going to go beyond Maxwell, because Maxwell, as I said, did not bring in electrodynamics beyond saying that H was a vorticity. Fitzgerald trained thoroughly in electrodynamics by studying the treatise, though he wasn't a Cambridge man, a little bit unusually at the time. immediately jumps in and takes one of the Maxwell equations, in this case the Ampere law, and he says if I identify H with a du dt, then this relationship in the Ampere law, and notice that there's no C over here, no conductivity here, no conduction current, says I'm going to be talking just about a dielectric at the moment. It follows then that the D vector has to have this form. It has to be the curl of this U vector. That comes directly from the Ampere law. This leads at once to two energy expressions. The energy expression for the kinetic energy from Maxwell now becomes something that looks like this, where the mu here comes from the relationship between B and H. It's a quadratic expression in the du dt. The W from E dot D, I'm sorry, this square here, this should be bracket here, becomes a quadratic expression in the curl of U. The epsilon goes down here in the denominator, and the mu goes up here in the numerator. It turns out if you wanted to talk that way, you could talk about mu as a density and as epsilon as an elasticity, but he doesn't, because it's irrelevant to the way the practice is going as to how you interpret those things physically. You now insert these two things into Hamilton's principle. Now, what is Hamilton's principle? There are various forms of it. The form that is canonically used by these people is the form we would use today, namely that if you integrate the difference between these two energies over a volume, and you further integrate that result between two states of the system at different times. A state A at some time t sub A, and a state B at some time t sub B. The system is going to evolve between those two states. And the way it evolved, according to Hamilton's principle, is such that if you take all possible such paths that the system will evolve between states A and B, that the variation of that result across all possible paths will yield one path, and that path in question will be the one in which the variation is zero. Actually, that yields two paths, but never mind that for the moment. Now, Fitzgerald takes a surface in which the parameters epsilon and mu change abruptly. The result is this integral, and it's hard to do this, separates, it's a volume integral in a continuum, into two parts. One part for one side of the surface and the other part for the volume on the other side. Each of the two resulting volume integrals can then be separated mathematically into a volume integral and a surface integral, with the surface integral applying at the interface as well as at infinity. Separately equating the volume and the surface integrals, that is the volume with the volume and the surface with the surface, then yields one, what you could call an equation of motion, and two, boundary conditions. What is the equation of motion that results? The Faraday law. You have now deduced the Faraday law from Hamilton's principle, assuming a continuum and taking the Ampere law as a constraint or a defining condition of the structure. You could do it the other way around. Use this one as a defining condition and get the Ampere law, and some people do later. In addition, you get a boundary condition. The boundary condition turns out to be the continuity in the tangent component of the continuity of the electric field, assuming certain other conditions here, which don't have to worry us. And this condition is sufficient to deduce the Fresnel ratios which govern the amplitudes of light reflected and refracted at a surface. This is the first such deduction in electrodynamics using Maxwell's type principles. Lorentz actually had done it 4 years before slightly differently, well, a lot differently. It yields what you already have got in optics since the time of Fresnel, the Fresnel ratio. So the first such deduction of that is done via Hamilton's principle. Now, the purpose of the paper was to get the Faraday and the Carr effects. So let's go on. let's take Maxwell's addition to the kinetic energy, which I showed you a few moments ago, for the Faraday effect. You add this term in to the energy. Taking Fitzgerald's identification of these variables, uninterpreted, turns that into something that looks like this. You just stick in his identification of these variables. You're not doing anything complicated. Then run that back all through Hamilton's principle. What do you get? And here it shows you what I started off by telling you a moment ago. You get a modification to one of Maxwell's equations. You have modified the Faraday law. That stands to reason. If you change the energy expression in Hamilton's principle, you're going to change the resulting equation of motion, if you will, in this case, the Faraday law. This is the addition that comes in to the Faraday law. If you put that together with the other Maxwell equations, you get a new wave equation. And that wave equation, though it has the h's in it, is exactly the same in form as the one that Maxwell had produced in the treatise by means of that business with vorticity and so on. Here deduced purely electrodynamically on the basis of a continuum structure. Now, this ought to already start puzzling people a little bit because the Faraday effect is, after Lorentz and so on, canonically an example of the interaction of electrons with an electromagnetic field passing through. And yet, here we have produced even in today's electrodynamics with electrons and so on, this is in fact the equation that governs the Faraday effect. And here we've done it without a word or thinking about anything microphysically, done purely on the basis of continuum beliefs. Now, it also alters the boundary conditions. It produces, instead of the one we had before, this very particularly complicated looking boundary condition there. Now that boundary condition, we'll see, can be interpreted in an interesting way, but the question is, does it work? Does it produce the effects on light reflected in the Carr effect that I told you about a few moments ago? Can you get that out of it? That's what the goal is here. And the answer to that is yes and no. You can get the production of ellipticity out of it. It will result. Linearly polarized light, when you use that boundary condition, will generate elliptically polarized light. But the axis of the elliptical polarization will not be rotated away from the previous linear polarization. And that was one of the two big discoveries of Carr. Why is that? Well, says Fitzgerald, the reason for that is I haven't put conductivity, sigma, into this thing. And I'm not going to put it in, says he, because you can't put it in and use Hamilton's principle. Hamilton's principle assumes a conservative system. As soon as you stick conductivity in there, you're in a non-conservative regime. There is a tricky way in which you could put it in. It's called the Rayleigh dissipation function, but it doesn't work with the variation techniques in the usual way. And if you're dealing with Hamilton's principle, you're not dealing with dissipation. And dissipation is a mystery anyway. We don't know what's going on down there. It's something strange. Who cares? Says maybe we can figure out how to deal with it. Now, just around this time, actually a couple of years later, another experimental discovery is made at Johns Hopkins in the United States by Hall, Edwin Hall, the student of Henry Rowland. Here's a scan from his actual experimental notebook. It's called the Hall effect. And by the way, the question of why things get called effects is an interesting one. Maybe we'll talk about that in a moment. So we think of the Hall effect as a manifestation of the Lorentz force on a charged particle in a magnetic field. Not how the Maxwellians or Hall think about it. Not at all. Because currents are not flows of particles. You can't think about it that way. Actually, there was a lot of discussion as to what happened originally, but the way in which this is thought about is the following. At first, Hall, exploring this, thinks that the action on his measured action on the current, what's the measured action? You put a piece of copper between a voltaic pile or a battery, you have a current running through it, you put a magnetic field perpendicularly to it, you stick a galvanometer across it, or a voltmeter for that matter, and you find if a galvanometer that you're getting a transverse current, if it's a voltmeter, you get a voltage difference across the two. We think of that as the deflection of charges by the magnetic field. He initially thought it had something to do with the direction of the voltaic source, but very rapidly he comes to the conclusion that actually what's going on is the generation of a new electric field. That somehow the interaction of the magnetic field applied with the electric field that's applied from the voltaic source produces in and of itself a new electric field, which however has a peculiar direction. A direction such that it is always orthogonal to both the current and the applied magnetic field, and what that does is it adds a slight component to what would otherwise be the electric field across the plate. This is a deeply Maxwellian way of thinking about things. A new continuous field is being generated here. Now the question is, can you take that notion and run with it to generate theory? Hall is no great mathematician, but his supervisor, Henry Rowland, is pretty good. Rowland had studied in both England and significantly in Berlin, actually. And he's the first to do so. And what does he do? He links it to the Faraday effect. Well, of course, the whole effect from our point of view is linked to the Faraday effect because both involve the motion of charged particles. But here it's going to be done in the context of Maxwellian practice. So what does he do? To the usual Maxwell field, he adds something that we'll call a Hall field. But, as usual, you can't deal with conduction, so you leave conduction out of it. Which is interesting, of course, since the only thing the Hall has discovered is what happens to a conduction current. But since a conduction current is supposed to be decaying displacement, if it's happening on the conduction current, it ought to happen on displacement. Because if it doesn't, then it shouldn't happen at all. So what does he do? He's not dealing with Hamilton's principle yet. He's exploring how to incorporate this. To the usual equation for the Faraday effect from Maxwell, he adds this term, where this little h is the applied magnetic field, and this is the displacement current. Again, note the absence of conductivity. That produces a new expression for the electric field. You have now changed one of Maxwell's equations directly. Keeping the other one and running the mathematics through produces this resulting wave equation, here expressed in terms of the vector potential. They indifferently give a wave equation in terms of the vector potential or the magnetic field or even the electric field. They don't care. But that expression is exactly the same in form as the one Maxwell had originally produced and that Fitzgerald had produced in 1879. Now done by adding a term designed to express the newly discovered effect that Hall had done. You're reaching for what? You're reaching for a unification structure here, is what you're trying to do with this system, bringing it all together. And that is thoroughly done by this man, Richard Tetley Glazebrook, in 1881, in which he links everything together completely well. He starts out with Maxwell's original expression, brings in field equations. I don't need to go through this except to show you the result. It gets a little complicated what he does. He produces a new expression for the Faraday effect, and now he goes to Hamilton's principle, sticks it all in Hamilton's principle, and comes up with a modification to one of the Maxwell equations, as usual, and a new boundary condition. And what? That boundary condition turns out to be exactly the same as the one that Fitzgerald had deduced several years before. You're reaching for a tight unification of all structures. The only problem you've got right now with all of this is that in the Carr effect you can't get the whole thing. Now, conductivity is at the issue here. Everybody knows that. These sets of results are widely read, and not just in Britain, but also in Germany and so on. And in Germany, in particular, they're only beginning to deal with Maxwell's equations after the production of electric waves by Heinrich Hertz in 1888. So they're still not entirely familiar with how to work with those things, but they rapidly become so. And this is going to be the first real work of Lorentz in electrodynamics. I won't mention what he did. Boltzmann's involved in this as well, and so on. Now, because the Carr effect seemed to require that conductivity be struck in there, several physicists decided to directly explore what the form of the equations would be. Forget Hamilton's principle for a moment, because everybody knows you can't do it in there, if you just stuck conductivity in directly. So there's a series of steps they all go through these same steps with slight variations. First, step one, add the whole field to the usual electric field. Step two, you can assume that the current is either just the displacement current or the displacement plus the conduction current. Remember, the British Maxwellians have only been dealing with this, but they know that something's going on. Step three, add in the whole field in such a way that you can wind up with a modified Faraday law. That modification will either include the total current or it'll just include the displacement current. Step four, to make a compact series of equations, both options can be accommodated by defining a complex index of refraction. That goes back to Cauchy, actually, in the 1830s, in which the conductivity, the angular frequency of a wave, the magnetic and electric permittivities enter in to form a complex index which has a real part r squared and an imaginary part 2 alpha. That expresses the effect of conductivity. It's well known, it's been widely utilized, it's unproblematic. And that way you can capture everything just by setting sigma to 0 or letting it be finite, and that results in this equation here. This is the canonical equation which results from the assumption that the Hall effect involves a new field. Everybody's doing this, even the non-Maxwellians, including Lorentz and Boltzmann. You add it in, you run everything through, you get a general wave equation. The question is, does it work? Lorentz included both of these terms in there. This was his first work in electrodynamics, first thorough work. His dissertation also deals with it in a slightly different way, but not this particular problem. J.J. Thomson in England and Paul Drude in Germany argue that the C here shouldn't be included. Let's see what happens. This leads to two different forms of the wave equation, which look like this. Both theories include conductivity in the sense that conductivity in J.J. Thomson and Drude appear for the metallic structure, but not for the extra term in the Hall effect. You leave out the conduction current and the Hall effect. I know it's getting a little complicated, but I'm going to get to the final effect here. The resulting equations are horrendous. I've never seen equations as complex as what this leads to. Approximations have to be made. Arguments can be had and were had over the nature of the approximations and so on. And out of these incredibly complicated equations, you have to generate empirically testable results. It's very, very hard. And they don't have computers, and they don't have little computing slaves to do this for them either. So it's really difficult to do this. And the equations get explored. And in Lorentz's laboratory in Leiden, he has students, postdocs in effect, or doctoral students, one in particular, now unknown, by the name of Remelt Sissing. And he produces a device to really test the Carr effect as accurately as possible. This device, by the way, was handed by him to Zeeman and used by Zeeman both for this and for the discovery of the Zeeman effect later on. It came out of these investigations originally. So this is the apparatus. You have a piece of metal here, a magnetic field, a polarizer. The light reflects off, comes through. That light then passes through an analyzer here and then gets looked at by this telescope over here. And then you can really very accurately observe things in this experiment. Two types of observations are performed. I don't need to go into that. Very rapidly, the results persuaded everybody, including Lorentz, that his equations were no good. It had to be rejected. That left only J.J. Thomson and Drude. And there were issues about that. Now, so this, and I'll conclude in a little bit, this brings me to these issues which are critical in physics when experiments in complicated situations are done of calculating errors and so on. As I said, they don't have computers. And they don't have a lot of people to do it. And Drude, in his equations, never calculated the resultant phases and amplitudes. He had an approximation system which went directly to the rotations. There's a problem with that. That actually hides, very strikingly, the effects of experimental error in this thing. And the reason for that is that depending on the type of experiments that are done when you set these polarizers and analyzers, it's either very sensitive to phase or very sensitive to amplitude. Now, critically, the theory depends more on phase than on amplitude. So if you don't calculate them separately, there's no way to really distinguish what's going on. This was the equation here. Now, notice that in this equation, you have this 2 alpha phase factor, which comes directly from metallic properties. It has nothing to do with the Hall effect or anything. It's what you usually have with metals. That factor, in the case of iron, which Sissing used, should be about 76 degrees 16 minutes. Now, from Sissing's result, in his experiments, it turns out to be 84 degrees 53 minutes. Now, this is in fact too large for accuracy, but you're not going to know that unless you actually calculate from deviations what the accuracy should be with phases. Drude never did that. He worked entirely with rotations and never tried an error calculation of any kind. Most people don't under any circumstances, and this would be particularly hard to do. So the result of that was argument. Drude got into a huge argument with people, one in particular, and another of Lorentz's students, Mr. Zeeman, called what's going on up there, what this phase has got to be, the Sissing phase, because it's this guy Sissing who discovered it. Another German physicist who was a specialist in metallic reflection gets into the game at this point, by the name of Eugen Goldhammer. And he said, I think that in order to accommodate what Sissing found, you have to stick an extra phase factor in there, which he just stuck in as a lambda, uninterpreted. Now that generated a bitter controversy between Drude and Goldhammer, because one, Drude's competence was being called into question by Goldhammer. It got really nasty, actually. And because if the phase had to be altered, then the entire deductive edifice, whether British or continental at this point, grounded in all cases on a continuum and structural analysis of how this works, no microphysics at all, then the entire deductive edifice begins to collapse, because you can no longer operate simply by adding terms to the field equations and assuming extensive parameters which are continuous. Drude knows that. Goldhammer's not involved directly with that sort of thing, so he doesn't care. Now here I've drawn a couple of graphs from their resulting equations of actually what the rotations would look like in these various theories. And this is a graph. These graphs are done for the experiments produced by Peter Zeeman, who was asked by Lorentz to use a different metal than what Sissing had done to explore this further. And he chose cobalt. The reason he chose cobalt was because cobalt has much higher complex components to the metallic reflection expressions than iron does, and so might be thought to generate a more significant effect. Now if you take a look at, now nobody's drawing graphs, except me here, so they never saw anything that looked like this. But the rotations actually look like this. So you choose 3 of the measurements, different situations, and one set of measurements runs completely along the line that would be predicted by Goldhammer's addition up there to the thing. And so the other one is very slightly off of it. And in all cases, they miss completely what happens if you just include displacement current in there. That's Drude, J.J. Thompson. Misses completely. Now, yeah, I'll be done in a second. Letters back and forth between Zeeman and Drude. Drude eventually concedes that he cannot accommodate the results that Zeeman has found. Now, why does he concede here? One, the deviation between theory of an experiment is 4 times as large as it was with iron. 2, Zeeman has calculated the actual rotations, which is the way Drude likes to do things. 3, Zeeman doesn't have any irons in this fire, unlike Goldhammer at the point, who had advanced the equation. Zeeman's just this little guy working in Lorentz's lab who's distanced from it, and he corresponds with Drude. It's all very polite. And Drude actually concedes, and this is a wrenching concession. Why is it wrenching? Because it means the end of continuum-based manipulations. At least Drude is the one who first says that, and in fact, that seems to be consensually thought across the board because it happens in Britain as well, within a year or two after this.
When was that?
These results, 1893. The existence of the extra phase called into question the very possibility of working purely macroscopically with the system by adding in an extra field. With that would go the entire practice of modifying the ether's fundamental equations, with matter being an emergent structure of the substratum, whose presence merely indicates that a given region of the ether has had its properties altered. Or at least this is what, and I have found no exceptions, within a year or two, everybody seems to think. Because British electrodynamic practice, grounded on modification of the Maxwell equations, stops dead within a year. And I don't find anything happening in Germany or France by people like Lorentz, or Poincaré for that matter, gets into the game slightly afterwards, that's any different. Now, and I will conclude now in a moment. Hertz, who was replaced in his first position at Kiel by Max Planck in 1879, had of course produced electromagnetic radiation at what we now call megahertz frequencies, vastly smaller than optical frequencies. Footnote, until then, Maxwellians in Britain thought you could not generate artificial electromagnetic radiation. That's a complicated story. It has to do with Fitzgerald's attempt to deal with the field equations for radiation, but, well, you can ask me that later. I can tell you why. It's complicated. In 1890, Hertz produces a series of diagrams which, in my opinion, are the single most influential set of diagrams that were produced in 19th century physics. It's the foundation of antenna theory. It's the ground for the way Max Planck begins to think about radiation electrodynamics subsequently. And in these diagrams, he has mapped out the radiation field of an oscillating dipole. But I want you to note that there's a little circle around the dipole here. That, you don't go into that circle. There is no theory for going into that circle at all. It's kind of like that event horizon that Helge was talking about there. That's terra incognita. This involves the introduction of what became known as the Hertz potentials and the calculation of the radiation field. Now, the very same year, and this is where I'll conclude, the very same year, and that the Goldhammer-Drude thing collapses with Zeeman, Hermann von Helmholtz, Hertz's Doktorvater, who's been very deeply involved with things, produces a new set of equations for electrodynamics which lie at the foundation of what will be introduced by Lorentz and others subsequently. And he's done this in order, in part, to capture an old discovery and to accommodate some of the new ones. Let me show you this. These are two equations that he had introduced on the basis of a mechanical model in the 1870s in order to accommodate a phenomenon known as anomalous dispersion. I'm not going to go into it. I just want to point out a structure. There was an equation here for the ether, usual equation for an elastic ether. He had added to it a term. That term involved both the ether's displacement and the displacement of an imaginary, if you will, material particle. That term, which is the difference between these two things, was added to the ether equation, and down here he had an equation for the material particle which involved an elastic restoring force on the particle, like it was tied to by a spring to a point, a dissipative force, which accommodates conductivity actually in anomalously dispersing bodies, and here a force equal and opposite to preserve Newton's third law as to what acted on the ether displacement. Those two equations lead to a set of results for anomalous dispersion which are successful. They work very, very well, but uninterpreted and difficult to put much a handle on. 1893, he transforms this under the influence of the story that I've been telling you, plus Hertz, into electromagnetic versions, and here we have the foundations of Lorentzian way of thinking about things. An equation of motion, in this case for the dipole oscillator, ionic moment, a restoring force, a dissipative force, and the electric driving force. From Maxwell's equations, the electric driving force with a term that refers back to the material structure, linking it directly